What is the universe? From quantum fields to cosmic fate. The Universe Explained. Have you ever looked up at the night sky and wondered what the universe truly is? Not just the stars you see, but the invisible fabric beneath them, the quantum fields humming with energy, the dark matter holding galaxies together, and the mysterious force pushing everything apart. What if the universe is not what it appears to be, but something far stranger, far more beautiful, and intimately connected to your very existence? Welcome to Sleep Entangled, where cosmology and serenity merge into contemplative voyages. If you find wonder in these explorations, remember to subscribe and let curiosity guide your nights. Now, settle in, breathe deeply, and enjoy this journey through the universe itself, from the smallest quantum whispers to the largest cosmic structures, from the explosive birth to the quiet death, from the deepest mysteries to the most profound questions. This is the complete story of everything. Chapter 1. The question of everything. What is the universe? It seems like such a simple question. A child asks it with pure wonder. A physicist asks it with equations. A philosopher asks it late at night, staring at the ceiling. Yet despite millennia of asking, the answer continues to evolve, deepen, and surprise us. The universe, in its most basic definition, is everything that exists. Every particle, every wave, every field, every force, every star you see and every galaxy beyond your sight, every moment of time from the infinite past to the infinite future, the space between atoms and the space between galaxy clusters, the thoughts in your mind and the neurons firing to create them, all of it, every single thing is the universe. But that definition, while technically correct, barely scratches the surface, because the universe is not merely a collection of things, it is a dynamic, evolving, interconnected whole. It is a fabric woven from spacetime itself. It is a sea of quantum fields vibrating with possibility. It is a story that began nearly 14 billion years ago and continues to unfold in ways we're only beginning to understand. Let us start with what we can observe. The observable universe, the portion of the cosmos from which light has had time to reach us, spans approximately 93 billion light-years in diameter. This staggering scale emerged not because space itself is that old, but because space has been expanding since the universe's birth. Light from distant galaxies has been travelling toward us for billions of years, yet in that time, those galaxies have moved even farther away due to cosmic expansion. We see them as they were, not as they are. Within this observable sphere exist roughly 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star potentially hosts planets. Each planet harbours atoms, and each atom is a universe unto itself, with electrons orbiting nuclei in clouds of probability. The scales are dizzying. The numbers defy comprehension. Yet all of it follows laws, patterns, symmetries that we can discover, test, and understand. Consider the scale for a moment. If the observable universe were reduced to the size of Earth, our entire Milky Way galaxy would be smaller than a dust mote. Our solar system would be invisible at the atomic level. You, standing on this metaphorical Earth-sized universe, would be far smaller than the smallest subatomic particle. Yet here you are, capable of comprehending these scales, of holding in your mind the vastness of cosmic structure. This is perhaps the greatest mystery of all, not that the universe is vast, but that something within it became capable of understanding that vastness. But the observable universe is likely just a tiny fraction of the total universe. Beyond our cosmic horizon, Beyond the distance light has travelled since the Big Bang, space continues. How far? We do not know. Perhaps infinitely. Perhaps the universe wraps back on itself like the surface of a sphere, finite yet without boundary. Perhaps there are other universes entirely, bubbling off from cosmic inflation like foam on an infinite ocean. We stand at the shore of knowledge, gazing at an endless sea. The universe also exists in time, not just space, but space-time, a four-dimensional fabric where past, present, and future are woven together. Einstein showed us that time is not absolute, not universal, not the same for everyone everywhere. Time bends near massive objects. It slows at high velocities. Two events simultaneous for one observer occur at different times for another. The universe does not merely exist in time. Time is part of what the universe is. This means the present moment is not universal. Right now, in your reference frame, is a different collection of events than right now in the reference frame of an astronaut orbiting Earth, or a particle racing through a collider, or a photon travelling across the cosmos. The universe does not have a single present tense. It has countless presents, layered and relative, depending on motion and gravity. When we speak of the universe's age, 13.8 billion years, we mean in a particular reference frame, averaged across cosmic observers at rest with respect to the cosmic microwave background. And beneath it all, beneath the stars and planets, beneath atoms and particles, lies something even more fundamental: quantum fields. These fields permeate every point in space, rippling with energy even in perfect vacuum. When these fields vibrate in specific ways, we perceive particles, electrons, photons, quarks. Matter and energy are not things floating in empty space, but patterns of oscillation in an underlying ocean of fields. You're not separate from the universe. You are the universe, localized, conscious, contemplating itself. The quantum field perspective transforms our understanding. Empty space is not empty. The vacuum seethes with virtual particles constantly appearing and disappearing, borrowing energy from uncertainty for fleeting instants. These quantum fluctuations are not theoretical abstractions. They have measurable effects. The Casimir effect, where two metal plates in vacuum attract due to excluded virtual particles, has been experimentally verified. Zero-point energy, the residual energy remaining at absolute zero temperature, is a consequence of quantum fields' irreducible activity. The universe at its deepest level is restless, never truly still, always vibrating with possibility. This chapter began with a question: what is the universe? But perhaps the deeper question is this: why does anything exist at all? Why is there something rather than nothing? Why these laws of physics and not others? Why is the universe comprehensible to minds like ours? These questions echo through every culture, every era, every contemplative moment. The ancient Greeks wondered about the arche, the fundamental substance from which everything emerges. Thales thought it was water, Anaximenes thought it was air. Heraclitus saw an eternal fire constantly transforming. Each was groping toward a profound truth. The universe is not static, not arbitrary, not meaningless. It is dynamic, lawful, and astonishingly fertile. The pre-Socratic philosophers recognized something we sometimes forget in our modern sophistication: that existence itself demands explanation. Why should there be laws at all? Why should mathematics describe reality? Why should the universe be knowable? These are not naive questions, but the deepest questions, and they remain, after all our scientific progress, fundamentally unanswered. Modern cosmology has given us tools the ancients could only dream of. Telescopes peer back to the universe's infancy, observing galaxies formed when the cosmos was less than 1 billion years old. Particle accelerators probe the quantum realm, recreating conditions that existed trillionths of a second after the Big Bang. Gravitational wave detectors listen to the ringing of spacetime itself, hearing the collisions of black holes billions of light-years away. We have measured the universe's age, 13.8 billion years. We have mapped its large-scale structure, a cosmic web of galaxy filaments separated by vast voids. We have detected the faint afterglow of creation itself, the cosmic microwave background still shimmering with photons released 380,000 years after the Big Bang. Yet with each answer, new mysteries emerge. We have discovered that the matter we see, stars, planets, gas, dust, constitutes less than 5% of the universe's total content. Approximately 27% is dark matter, invisible yet gravitationally powerful, holding galaxies together. The remaining 68% is dark energy, a mysterious force accelerating the universe's expansion. We live in a cosmos where 95% of the content is unknown. We are children at the edge of a vast forest, seeing only the nearest trees. Imagine for a moment standing on a mountaintop at night far from city lights. Above you, the Milky Way arches across the sky, a river of stars, a band of light formed by billions of distant suns. You're looking at your galactic home from the inside, a spiral arm resident gazing toward the dense core. Every star you see is a neighbour, relatively speaking, within a few thousand light-years. The nearest star beyond our Sun, Proxima Centauri, is 4.24 light-years away. The farthest star visible to your naked eye, V762 Cas, is approximately 16,000 light-years distant. Yet all of them, every single one, resides within the Milky Way. Beyond our galaxy lie others. Andromeda, our nearest large galactic neighbour, is 2.5 million light-years away, approaching us at 110 kilometers per second. In approximately 4 billion years, the Milky Way and Andromeda will collide, merge, and form a new elliptical galaxy that astronomers have already named Milkomeda. This is the universe at work, dynamic, violent, creative, indifferent to our presence, yet giving rise to structures capable of contemplating it. And at the grandest scales, galaxies cluster together. Our local group contains more than 50 galaxies. The local group is part of the Virgo supercluster, a structure spanning 110 million light-years. The Virgo supercluster is itself part of Laniakea, a supercluster of superclusters containing approximately 100,000 galaxies and stretching 500 million light-years across. These structures form a web, with galaxies concentrated along filaments and walls, separated by enormous voids where almost nothing exists. This is the universe's architecture, not random, not chaotic, but sculpted by gravity over billions of years. So, as you rest, as you drift deeper into this contemplative journey, let this thought settle gently into your awareness. The universe is not merely something you live within. You are made of it. The calcium in your bones formed in dying stars. The iron in your blood forged in supernova explosions. The hydrogen in your water dates to the universe's first minutes. Your stardust contemplating stars, atoms aware of atoms, the cosmos awakening to itself. This is not metaphor. This is physics. Beautiful, precise, and deeply mysterious. Now let us explore the foundations. Let us begin with the fabric itself. Chapter 2. The Fabric of Spacetime, 14 to 28. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would forever change humanity's understanding of reality. Albert Einstein, working in relative obscurity, proposed something radical. Space and time are not separate, absolute entities but aspects of a unified whole, space-time. This was not philosophy, it was physics, testable and precise. Einstein's special theory of relativity began with two simple postulates. First, the laws of physics are the same for all observers moving at constant velocity. Second, the speed of a light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. These innocent-sounding principles led to astonishing conclusions. Time is not universal. Two observers moving relative to each other will disagree about the duration of events and even the simultaneity of distant happenings. A traveller moving near the speed of light ages more slowly than a stationary observer, not because of some mechanical effect on clocks, but because time itself passes differently. This is time dilation, verified countless times in experiments with atomic clocks, particle accelerators, and GPS satellites orbiting Earth. The twin paradox illustrates this beautifully. Imagine twins, one remaining on Earth, while the other travels to a distant star at 99% light speed. From Earth's perspective, decades pass. The travelling twin's clock runs slowly, aging only a few years during the journey. Upon return, the travelling twin is genuinely younger, not through deception or illusion, but because time genuinely passed more slowly in the travelling reference frame. This is not science fiction, this is tested physics. Space is not absolute either. Lengths contract in the direction of motion. A ruler rushing past you appears shorter than when at rest, though not from any physical compression. Space itself is relative. Mass and energy are equivalent, related by Einstein's famous equation, E equals mc squared. Mass is frozen energy. Energy has mass. They are two forms of the same thing. But this was only the beginning. In 1915, Einstein completed his general theory of relativity, extending these ideas to gravity. Newton had described gravity as a force, an invisible pull between massive objects. Einstein revealed something deeper. Gravity is not a force at all. Gravity is the curvature of space-time itself. Imagine space-time as a vast flexible fabric. Place a massive object like the Sun on this fabric, and it creates a depression, a curvature. Planets do not orbit because the Sun pulls them. They orbit because they follow the curved paths, geodesics, through the bent space-time around the Sun. They are moving in straight lines through curved space, much as an airplane flies a curved path over Earth's spherical surface, while maintaining a straight heading. This is not mere analogy. Space-time genuinely curves. Einstein's field equations describe precisely how matter and energy curve space-time, and how curved space-time tells matter and energy how to move. As physicist John Archibald Wheeler elegantly summarized, space-time tells matter how to move, matter tells space-time how to curve. The consequences are extraordinary. Light, having no mass, still follows space-time's curvature. A photon passing near the Sun bends its trajectory, an effect first confirmed during the solar eclipse of 1919 by Arthur Eddington. This gravitational lensing is now routinely observed. Distant galaxies behind massive galaxy clusters appear distorted, stretched into arcs and rings, their light bent by intervening gravity. Time itself curves. Clocks run slower in gravitational fields. A clock on Earth's surface ticks more slowly than one in orbit, not because of mechanical differences, but because time near a massive object genuinely passes more slowly. GPS satellites must correct for this relativistic effect, approximately 38 microseconds per day. or navigation errors would accumulate rapidly. Your phone's GPS works because general relativity is correct. Spacetime can ripple. Einstein predicted gravitational waves, distortions in spacetime propagating at light speed, generated by accelerating masses. For a century, these waves remained hypothetical. Then, on September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples from two colliding black holes 1.3 billion light-years away. Spacetime itself stretched and compressed by 1,000th the width of a proton as the wave passed Earth. We had heard the universe singing. Since that first detection, LIGO and Virgo have observed dozens of black hole mergers, neutron-star collisions, and exotic events. On August 17, 2017, LIGO detected gravitational waves from two neutron stars colliding. Telescopes worldwide swung into action, observing the resulting kilonova, an explosion that forged gold, platinum, and uranium, solving the long-standing mystery of where heavy elements form. This was multi-messenger astronomy. Gravitational waves, light, gamma rays, radio waves all telling the same story. Black holes represent spacetime's most extreme curvature. When a massive star collapses, if nothing can halt its gravitational compression, it forms a singularity, a point of infinite density where space-time curvature becomes infinite. Surrounding the singularity is the event horizon, a boundary beyond which escape velocity exceeds light speed. Nothing, not even light, can cross this threshold outward. Time stops at the event horizon, at least from an external observer's perspective. The fabric tears, folds upon itself, creates a one-way door into oblivion. Yet, even black holes are not entirely black. In 1974, Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation, slowly evaporating over inconceivable timescales. A stellar mass black hole takes 10 to the 67th power years to evaporate, far longer than the current age of the universe, but eventually even these cosmic monsters will dissolve into Hawking radiation, returning their energy to the universe. The geometry of spacetime depends on the universe's total energy density. If the density exceeds a critical value, spacetime curves back on itself, creating a closed universe, finite in volume yet without boundary, like the surface of a sphere. If the density is below critical, spacetime curves negatively, forming an open universe extending infinitely. If the density equals the critical value exactly, spacetime is flat, Euclidean geometry holds on cosmic scales, and parallel lines never meet. Observations suggest our universe is remarkably close to flat, so close that we cannot yet determine with certainty whether it is exactly flat or slightly curved in either direction. This flatness is itself mysterious, requiring extraordinary fine-tuning in the universe's early moments. The inflationary theory, which we will explore shortly, offers an explanation. Rapid exponential expansion flattened space-time much as inflating a balloon flattens its surface. And think of space-time as an ocean, not metaphorically but as a genuine medium. Particles are waves on this ocean. Gravity is the ocean's currents and tides. Black holes are whirlpools. Gravitational waves are ripples spreading from cosmic collisions. And the Big Bang? That was the moment the ocean began. Not an explosion into space, but the eruption of space and time themselves from what? We do not know. Physics breaks down at that singular point. Our equations yield infinities, meaningless results. We stand at the boundary of knowledge. Einstein spent the latter decades of his life seeking a unified field theory, hoping to unify gravity with electromagnetism to reveal a deeper geometric structure underlying all forces. He did not succeed. That quest continues today through string theory, loop quantum gravity, and other approaches attempting to reconcile general relativity with quantum mechanics. We know both theories are correct in their domains, yet they contradict each other at extreme scales. Inside black holes, at the Big Bang, at the Planck length of 10 to the negative 35th meters. Something profound awaits discovery. So, as you rest, as you allow these concepts to drift gently through your awareness, imagine yourself not sitting on solid ground but floating on a dynamic fabric. Space-time itself, subtle and flexible, curved by every mass, rippling with passing waves, connecting every event in cosmic history. You are not in the universe. You're a pattern in space-time, a localized curvature, a conscious awareness woven into the fabric of existence. Now, let us go deeper still, beneath space-time itself, to the quantum foundation where reality becomes even stranger and more beautiful. Chapter 3. The Quantum Foundation, 28 to 42. If general relativity describes the cosmos at its larger scales, quantum mechanics governs the smallest. These two theories are humanity's greatest intellectual achievements, yet they fundamentally contradict each other. General relativity is deterministic. Given initial conditions, the future unfolds with precision. Quantum mechanics is probabilistic. Outcomes are uncertain until observed, existing in superposition until measurement collapses possibilities into actuality. At the heart of quantum mechanics lies a profound mystery: wave-particle duality. Light, long thought to be a wave, exhibits particle-like properties. Matter, seemingly solid and localized, displays wave-like behavior. Nothing is simply one or the other. Everything is both, simultaneously, until you force it to choose. The story begins in 1900 with Max Planck, who solved a troubling problem in classical physics, the ultraviolet catastrophe. Classical theory predicted that hot objects should emit infinite energy at short wavelengths, clearly absurd. Planck proposed a radical solution. Energy is quantized, coming in discrete packets he called quanta. The energy of a quantum is proportional to frequency, E equals hf, where h is Planck's constant, a fundamental number woven into the fabric of quantum reality. Einstein extended this idea in 1905, proposing that light itself consists of particles, photons, each carrying energy in quantized packets. This explained the photoelectric effect. When light strikes metal, it ejects electrons, but only if the light's frequency exceeds a threshold. Classical waves should dislodge electrons regardless of frequency, given sufficient intensity. Photons provided the answer. Each photon delivers a discrete kick of energy. Low-frequency photons lack sufficient energy per particle, regardless of how many strike the surface. But light is also a wave. Thomas Young's double-slit experiment in 1801 had demonstrated this conclusively. When light passes through two narrow slits, it creates an interference pattern, alternating bright and dark bands, on a screen beyond. Waves from each slit overlap, reinforcing where peaks align, cancelling where peaks meet troughs. Only waves interfere. Particles would create two bands corresponding to the slits. The paradox deepened in 1924 when Louis de Broglie proposed that matter too exhibits wave properties. Every particle has an associated wavelength, inversely proportional to its momentum. Lambda equals h over p. Electrons, atoms, even baseballs have wavelengths. though for macroscopic objects the wavelengths are so small as to be undetectable. In 1927, Clinton Davison and Lester Germer confirmed de Broglie's hypothesis by firing electrons at a crystal and observing diffraction patterns, electrons acting as waves. The double-slit experiment, repeated with electrons, reveals the heart of quantum strangeness. Send electrons one at a time through two slits. Each electron strikes the detector screen at a single point, like a particle. Yet over time, the accumulated points form an interference pattern, characteristic of waves. Each electron somehow interferes with itself, as if passing through both slits simultaneously, exploring multiple paths, existing in a superposition of possibilities. Observe which slit the electron traverses, and the interference pattern vanishes. The electron behaves like a particle when watched, a wave when not. Observation itself affects reality, collapsing the wave function, forcing nature to choose one outcome from many possibilities. This is not an instrumental effect, not a disturbance caused by clumsy measurement. It is fundamental. Before observation, the electron genuinely exists in a superposition of states. Observation creates definite reality. Niels Bohr developed the Copenhagen interpretation to make sense of this. The wave function, described by Schrödinger's equation, evolves deterministically, encoding probabilities for all possible outcomes. Upon measurement, the wave function collapses, and one outcome manifests. Bohr introduced complementarity. Wave and particle are complementary aspects of a deeper reality. Which aspect manifests depends on how you look. Ask a wave question. Perform an interference experiment, and nature answers with waves. Ask a particle question. Measure position, and nature answers with particles. Werner Heisenberg formalized the limits of knowledge with his uncertainty principle. Certain pairs of properties, position and momentum, energy and time, cannot both be known precisely. The more accurately you measure one, the less accurately you can know the other. This is not experimental limitation, it is fundamental. Delta x delta p greater than or equal to h bar over 2, where h bar is the reduced Planck constant. Particles do not have definite positions and momenta simultaneously. Such precision does not exist in nature. The quantum realm is not deterministic chaos. It is governed by precise mathematical laws, Schrödinger's equation, Heisenberg's matrix mechanics, Dirac's formulation incorporating relativity. Yet these laws describe evolution of probabilities, not certainties. Einstein famously objected, stating, "God does not play dice." Bohr reportedly replied, "Stop telling God what to do." The debate raged for decades. Experiments have sided with Bohr. Quantum mechanics is not incomplete or approximate, it is fundamental. But beneath even quantum mechanics lies something deeper. Quantum field theory. Particles are not fundamental entities but excitations in underlying fields. An electron is a ripple in the electron field. A photon is a vibration in the electromagnetic field. Quarks emerge from quark fields. Every point in space hosts every field, vibrating with zero-point energy even in perfect vacuum. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed quantum electrodynamics, QED, describing interactions between light and matter with extraordinary precision. QED predicts the electron's magnetic moment to 10 decimal places, matching experiments exactly. It is the most precisely verified theory in physics. Paul Dirac predicted antimatter from combining quantum mechanics with relativity. Carl Anderson discovered the positron in 1932, confirming Dirac's astonishing prediction. The Standard Model of particle physics extends these ideas, describing 3 of the 4 fundamental forces: electromagnetism, weak nuclear force, strong nuclear force, through quantum fields. The Higgs field, confirmed in 2012 at CERN's Large Hadron Collider, gives particles mass through their interaction with this pervasive field. Particles moving through the Higgs field are like swimmers moving through water. Resistance creates effective mass. Quantum mechanics reveals that reality is not made of things but of relationships, probabilities and transformations. The universe is not a collection of objects but a network of interactions between fields. Particles as temporary patterns, emerging and dissolving, borrowing energy from vacuum fluctuations for fleeting instants. The distinction between something and nothing blurs at quantum scales. This has profound implications for the universe's birth. At the Planck time, 10 to the minus 43 seconds after the Big Bang, quantum effects dominated. Space and time themselves fluctuated, foamed, dissolved into quantum uncertainty. Classical space-time did not yet exist. General relativity cannot describe this era. We need a quantum theory of gravity, still elusive despite decades of effort. Think of the quantum foundation as a vast shimmering sea beneath the surface of classical reality. Atoms, molecules, cells, stars, galaxies, all emerge from this quantum substrate, where nothing is certain, everything fluctuates, and observation creates reality. You're not separate from this quantum sea. Your neurons rely on quantum chemistry. Your vision begins with photons triggering quantum transitions in retinal molecules. Your thoughts, conscious awareness itself, may involve quantum processes in microtubules within neurons, as Roger Penrose and Stuart Hameroff propose in Orchestrated Objective Reduction. So as you drift, as you rest in contemplation, let this understanding wash gently over you. The universe is built not on solid foundations but on probabilities and potentials, on fields vibrating with infinite possibility. Reality is participatory. The cosmos does not exist independent of observation. In some deep sense, the universe requires conscious observers to become fully real. You're not merely witnessing reality, you are helping to create it. Now, let us witness the universe's birth, the moment spacetime and quantum fields erupted into existence. Chapter 4 of The Birth, Big Bang and Inflation, 42 minutes to 56 minutes and 30 seconds. In the beginning, or as close to it as physics can reach, the universe was unimaginably hot, dense, and small. Not an explosion into pre-existing space, but the eruption of space and time themselves. The Big Bang was not an event in the universe, it was the birth of the universe. The evidence for the Big Bang is overwhelming. In 1929, Edwin Hubble discovered that distant galaxies are receding from us, and the farther away they are, the faster they move. This is not galaxies flying through static space, but space itself expanding, carrying galaxies along like raisins in rising bread dough. If space is expanding now, it was smaller in the past. Trace this expansion backward, and everything converges to a singular point, the Big Bang singularity. In 1948, George Gamow, Ralph Alpher, and Robert Herman predicted that if the universe began hot and dense, it should have cooled as it expanded, leaving behind a faint glow, the cosmic microwave background, CMB. In 1965, Arno Penzias and Robert Wilson accidentally discovered this radiation. The entire sky glows with microwave photons at 2.725 Kelvin, remnants from when the universe was 380,000 years old and atoms first formed. This is the oldest light we can see, the afterglow of creation. But let us begin at the true beginning, or as near as physics allows. At time zero, the universe was infinitely hot, infinitely dense, a singularity where general relativity breaks down and quantum effects dominate. We cannot describe this moment. At the Planck time, 10 to the minus 43 seconds after the singularity, the universe was 10 to the 32 Kelvin, and quantum fluctuations in spacetime itself were significant. Space and time foamed and fluctuated. Perhaps the universe emerged from a quantum vacuum fluctuation, a spontaneous eruption of something from nothing, borrowing energy from the vacuum and inflating before the debt came due. At 10 to the minus 36 seconds, something extraordinary occurred. Cosmic inflation. The universe underwent exponential expansion, doubling in size every 10 to the minus 37 seconds, driven by a hypothetical inflaton field in a high-energy false vacuum state. In a fraction of a second, the universe grew from subatomic scales to perhaps the size of a grapefruit, or much larger. This inflationary epoch solved several puzzles. First, the horizon problem. Distant regions of the universe that seemingly never contacted each other have the same temperature, visible in the CMB's uniformity. How did they come to thermal equilibrium? Inflation answers. They were once close enough to equilibrate, then inflated to vastly separated regions. Second, the flatness problem. The universe is remarkably flat, requiring extraordinary fine-tuning of initial conditions. Inflation explains this naturally. Exponential expansion flattens spacetime, much as inflating a balloon flattens its surface. Third, the monopole problem. Grand unified theories predict massive magnetic monopoles should have formed in the early universe, yet none are observed. Inflation dilutes them to undetectability. Alan Guth proposed inflation in 1980. Andre Linde, Paul Steinhardt and Andreas Olbrecht refined the theory. Inflation is not proven, but it elegantly explains features otherwise mysterious. Moreover, quantum fluctuations during inflation, tiny ripples in the inflaton field, seeded the density variations that eventually grew into galaxies. These primordial fluctuations are imprinted in the CMB, detected by the COBE, WMAP, and Planck satellites. We see the quantum seeds of cosmic structure stretched to astronomical scales by inflation. After inflation ended, approximately 10 to the negative 32nd seconds after the Big Bang, the inflaton field decayed, releasing its energy as particles and radiation. The universe reheated to immense temperatures, now filled with a hot, dense plasma of quarks, gluons, electrons, photons, and neutrinos. This is the radiation-dominated era. At 10 to the minus 12 seconds, the temperature dropped to 10 to the 15th Kelvin, and the Higgs field underwent a phase transition, acquiring a non-zero vacuum expectation value. Particles interacting with the Higgs field gained mass. Fundamental forces began to separate. Electromagnetism split from the weak nuclear force, manifesting as distinct interactions. At 10 to the minus 6 seconds, 1 microsecond after the Big Bang, quarks bound together to form protons and neutrons, the building blocks of atomic nuclei. This is the quark-hadron transition. The universe was now a soup of protons, neutrons, electrons, photons, and neutrinos, still far too hot for atoms to form. At 1 second, the temperature had dropped to 10 billion Kelvin, still hotter than any star's core. Neutrinos, having interacted weakly with matter, decoupled and streamed freely through the universe. Today, these relic neutrinos permeate space, outnumbering atoms 1 billion to 1, though detecting them remains extraordinarily difficult. Between 1 and 3 minutes after the Big Bang, temperatures fell to where nuclear fusion could occur. Protons and neutrons fused into deuterium, helium-3, helium-4, and trace amounts of lithium. This is Big Bang nucleosynthesis. Approximately 25% of the universe's ordinary matter became helium, with the rest remaining hydrogen. These abundances, predicted by Ralph Alpher and Robert Herman, and confirmed by observations, provide powerful evidence for the hot Big Bang model. For the next 380,000 years, the universe remained opaque. Photons constantly scattered off free electrons unable to travel far. This is the photon-baryon plasma era. The universe glowed like the interior of a star, gradually cooling as it expanded. At 380,000 years, a critical threshold was crossed. The temperature dropped to approximately 3000 Kelvin, cool enough for electrons to bind with nuclei, forming neutral atoms. This is recombination. With free electrons gone, photons could travel unimpeded. The universe became transparent. The photons released at that moment, stretched by cosmic expansion from visible light to microwaves, are the cosmic microwave background we observe today. We see the universe as it was 380,000 years old, the moment it became transparent, the oldest light possible. The CMB is astonishingly uniform, 2.725 Kelvin in every direction to 1 part in 100,000. Yet subtle variations exist, detected first by Kobe in 1992 and mapped in exquisite detail by Dugmap and Planck. These variations, temperature differences of mere millionths of a degree, represent density fluctuations seeded during inflation. Denser regions would collapse under gravity, forming the first stars and galaxies. The CMB is a baby picture of the universe, showing the seeds of all structure. After recombination, the universe entered the Dark Ages. No stars yet existed to produce light. For hundreds of millions of years, space was filled with neutral hydrogen gas, dark and cold, slowly clumping under gravity's patient pull. But gravity is relentless. Denser regions attracted more matter, growing denser still until the first stars ignited. Approximately 100 to 200 million years after the Big Bang, the first generation of stars, population 3 stars, formed. These were massive, short-lived, and composed purely of hydrogen and helium. No heavier elements existed yet. These stars burned ferociously, fusing hydrogen into helium, helium into carbon, carbon into oxygen, and on through the periodic table up to iron. When they exhausted their fuel, they exploded as supernovae, scattering newly forged elements into space and seeding the universe with the raw materials for planets and life. These supernovae also produced elements heavier than iron, gold, platinum, uranium through rapid neutron capture. Every atom heavier than hydrogen and helium in your body formed inside stars or during their explosive deaths. You're made of stardust, a poetic truth that is also literal scientific fact. The first stars reionized the hydrogen gas, ending the Dark Ages and beginning the era of cosmic reionization. The universe became transparent again, though now filled with ionized plasma rather than neutral atoms. Galaxies formed, merging and growing. The cosmic web began to take shape, filaments of galaxies separated by vast voids. So, as you rest, as you drift through this narrative of origins, let this reality settle gently into your awareness. You exist because the universe began. The atoms in your body formed in the Big Bang's first minutes or inside stars billions of years later. The galaxies you see emerge from quantum fluctuations during an inflationary epoch lasting less than a blink. The light reaching your eyes travelled for billions of years, bringing news of ancient events. You're not merely in the universe, you're a part of its history, a conscious chapter in a cosmic story still unfolding. Now, let us explore the architecture this history built, the large-scale structure of the cosmos. Chapter 5. The architecture, large-scale structure, 5630 to 7030. Zoom out far enough, and the universe reveals its architecture, not random, not chaotic, but organized into a vast cosmic web. Galaxies cluster along filaments, forming walls and sheets that surround enormous voids where almost nothing exists. This is the large-scale structure sculpted by gravity over billions of years. Galaxies are not scattered uniformly through space. They congregate in groups and clusters. Our Milky Way belongs to the local group, containing more than 50 galaxies, dominated by the Milky Way and Andromeda. Smaller galaxies, dwarf spheroidals, irregulars, orbit these giants like moons around planets. Galaxy clusters are larger still, containing hundreds or thousands of galaxies bound by mutual gravity. The Virgo cluster, approximately 54 million light-years away, contains over 1,000 galaxies. The Coma cluster harbours more than 1,000 galaxies in a region 15 million light-years across. These clusters are among the universe's largest gravitationally bound structures. In the 1980s, astronomers discovered something unexpected. Clusters themselves cluster into superclusters, structures spanning hundreds of millions of light-years. The Virgo supercluster, containing our local group, spans 110 million light-years and includes thousands of galaxies. But even superclusters are not the end. In 2014, a team led by Brent Tully mapped our cosmic neighbourhood and identified Laniakea, a supercluster of superclusters containing approximately 100,000 galaxies and extending 500 million light-years. Laniakea, Hawaiian for immeasurable heaven, is our cosmic address at the grandest scales, and Laniakea is just one of countless such structures, and between these structures lie voids, vast regions with few galaxies, sometimes spanning hundreds of millions of light-years. The Brutus Void, discovered in 1981, is approximately 330 million light-years in diameter and contains only 60 galaxies where 10,000 might be expected. These voids are not completely empty but contain far less matter than average, like bubbles in foam. The cosmic web resembles a sponge or neural network, dense nodes connected by filaments surrounding voids. This structure emerged from tiny density fluctuations in the early universe, amplified by gravity. Denser regions attracted more matter, growing denser still. Less dense regions lost matter to their neighbours, becoming voids. Over billions of years, this process carved the cosmic web we observe today. Computer simulations model this evolution beautifully. Start with initial conditions matching the CMB fluctuations, apply known physics, and watch structure emerge. The Millennium simulation, run in 2005, tracked billions of particles evolving over cosmic time, producing synthetic universes remarkably similar to our own. This is powerful validation. We understand how structure forms, but there is a mystery. Galaxies rotate too fast. Stars in the outer regions of spiral galaxies orbit at speeds that should fling them into intergalactic space, given only the visible matter's gravity. Yet galaxies remain intact. In the 1970s, Vera Rubin and Kent Ford measured rotation curves of spiral galaxies and found them flat. Stars at all distances orbit at similar speeds, contrary to Newtonian predictions. Something unseen, something massive, holds galaxies together. This is dark matter. It does not emit, absorb, or reflect light. It interacts gravitationally but not electromagnetically. We detect it only through its gravitational influence, holding galaxies together, bending light through gravitational lensing, contributing to the universe's overall mass-energy budget. Observations suggest dark matter constitutes approximately 27% of the universe's total content, outweighing ordinary matter 5 to 1. What is dark matter? We do not know. Candidates include WIMPs, weakly interacting massive particles, predicted by supersymmetric theories but not yet detected despite decades of searching. Axions, hypothetical particles originally proposed to solve a problem in quantum chromodynamics, are another possibility. Machos, massive compact halo objects like brown dwarfs or black holes, could contribute but cannot account for all dark matter. Primordial black holes, formed in the Big Bang's first moments, remain an intriguing possibility. We are searching, but dark matter's identity remains elusive. Dark matter's distribution follows the cosmic web, forming halos around galaxies, scaffolding upon which visible matter settles. Computer simulations show that without dark matter, galaxies would not form. Gravity from ordinary matter alone is insufficient to overcome cosmic expansion and collapse into bound structures. Dark matter provided the gravitational wells into which gas could fall, condense, and ignite as stars. In a deep sense, we owe our existence to this invisible substrate. Galaxy clusters also reveal dark matter through gravitational lensing. Massive clusters bend spacetime, distorting the appearance of background galaxies. The Bullet cluster, two colliding galaxy clusters, provides striking evidence. Visible matter, hot gas emitting X-rays, slowed and lagged during the collision. Dark matter, interacting only gravitationally, passed through unimpeded. Gravitational lensing reveals dark matter's position, offset from the visible gas. This is direct evidence that dark matter exists and behaves as predicted. The largest structures, filaments, walls, superclusters, trace dark matter's distribution. Galaxies are merely bright markers, like city lights revealing population density at night. The true mass resides in dark matter halos, invisible but gravitationally dominant. We see the universe's skeleton, not its flesh. Imagine the cosmic web as a vast neural network, with galaxies as neurons, filaments as axons connecting them, and voids as the spaces between. This is not mere metaphor. The statistical properties of the cosmic web resemble neural networks. Some researchers speculate this hints at deeper principles, perhaps suggesting the universe itself processes information in ways analogous to consciousness. This remains speculative, but the resemblance is striking. The cosmic web is dynamic, not static. Galaxies collide and merge, clusters attract new members, filaments grow and interconnect. Over time, structure grows increasingly complex, though dark energy, which we'll explore shortly, is accelerating expansion and will eventually halt this growth, fragmenting the web. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the cosmic web's intricate structure. We see it in 3 dimensions, tracing it across billions of light years and billions of years of cosmic history. This is one of humanity's great intellectual achievements, mapping the universe itself. As you rest, as you gently drift, imagine yourself embedded in this cosmic web, a galaxy resident, an inhabitant of Laniakea, connected by invisible filaments to clusters and superclusters across the observable universe. The gravitational pull of distant structures influences our motion, just as we influence theirs. The universe is not a collection of isolated objects, but a deeply interconnected whole, woven by gravity, held together by dark matter and illuminated by the stars that, like you, are participants in this grand cosmic architecture. Now, let us turn our attention to the invisible components, dark matter and dark energy that dominate the universe yet remain profoundly mysterious. If you're still with me in this late-night exploration of the cosmos, you're part of something rare. Curious minds willing to drift through the deepest mysteries of existence. A quick subscribe helps others find this contemplative journey through the universe's secrets. Now let's continue deeper into the invisible forces shaping reality itself. Chapter 6. The Invisible Universe, Dark Matter and Dark Energy, 7030 to 8430. 95% of the universe is invisible to us, not hidden by dust or distance, but fundamentally non-luminous. Dark matter and dark energy, the dominant components of cosmic reality, must just sticky. We have discussed dark matter's role in holding galaxies together and scaffolding the cosmic web, but dark energy is even stranger. In 1998, two teams, the Supernova Cosmology project led by Saul Perlmutter and the High Z Supernova Search team led by Brian Schmidt and Adam Rees, made an astonishing discovery. The universe's expansion is accelerating. Distant supernovae appeared dimmer than expected, implying they were farther away than predicted by models assuming constant or decelerating expansion. Something is pushing the universe apart. This something is dark energy, comprising approximately 68% of the universe's total content. Dark energy does not clump like matter or dark matter. It is smoothly distributed through space, exerting negative pressure, a repulsive gravitational effect. As the universe expands, dark energy density remains constant. More space means more dark energy, driving ever faster expansion. The simplest explanation is Einstein's cosmological constant lambda, which Einstein introduced in 1917 to allow a static universe solution to his field equations. When Hubble discovered cosmic expansion, Einstein called the cosmological constant his biggest blunder and abandoned it. Yet in 1998, it returned. Perhaps the vacuum itself possesses energy, zero-point energy from quantum fields, and this vacuum energy is the cosmological constant. Quantum field theory predicts vacuum energy, but calculations yield a value 10 to the 120 times larger than observed. This is the cosmological constant problem, one of physics' greatest mysteries. Why is vacuum energy so small yet non-zero? We do not know. Perhaps our calculations are wrong. Perhaps unknown cancellations occur. Perhaps dark energy is not the cosmological constant but something else. Quintessence, a dynamical field evolving over time. Dark energy's consequences are profound. If it remains constant, the universe will expand forever, accelerating eternally. Galaxy clusters will disperse. Distant galaxies will recede beyond our cosmic horizon, their light redshifted to undetectability. Eventually, only our local group, Milky Way and Andromeda merged into Milkomeda, will remain visible. Trillions of years from now, astronomers in Milkomeda will see only their galaxy surrounded by darkness, with no evidence that a larger universe ever existed. The far future is bleak yet fascinating. Stars will exhaust their fuel. Red dwarfs burning hydrogen slowly will shine for trillions of years, but even they will eventually fade. The universe will enter the degenerate era dominated by stellar remnants, white dwarfs, neutron stars, black holes. Brown dwarfs, failed stars will briefly shine as they collapse, radiating gravitational energy as heat. In 10 to the 40 years, if protons decay as some theories predict, even white dwarfs and neutron stars will dissolve into radiation. the black hole era will begin, dominated by these gravity wells. Hawking radiation causes black holes to evaporate, but this process is astonishingly slow. A solar mass black hole takes 10 to the 67th power years to evaporate. Supermassive black holes in galaxy centers take 10 to the 100 years or longer. Eventually, even black holes vanish, leaving only the dark era, a cold, dark, dilute universe of photons, neutrinos, and electrons, separated by ever-growing distances, approaching absolute zero. This is heat death, the maximization of entropy, the end of structure, complexity, and information. The universe becomes featureless, uniform, dead. Yet this bleak future is trillions of years away. For now, the universe is vibrant, alive with stars, galaxies, and complex structures. Life emerged, consciousness arose, and minds capable of understanding the cosmos came into being. This is the universe's brief flourishing, a moment between the hot Big Bang and the cold heat death, but return to dark matter and dark energy's mystery. We have named them but not understood them. They dominate the universe yet elude direct detection. Dark matter interacts gravitationally, but efforts to detect it directly, through WIMPs scattering off nuclei in underground detectors, have so far yielded null results. Either dark matter particles are more elusive than predicted, or our understanding is incomplete. Alternative theories exist. Modified Newtonian dynamics, MOND, proposed by Mordechai Milgrom in 1983, suggest gravity behaves differently on galactic scales, eliminating the need for dark matter. However, MOND struggles to explain gravitational lensing and large-scale structure without invoking invisible matter. Most physicists favor dark matter, supported by multiple independent lines of evidence. Dark energy remains even more enigmatic. If it is vacuum energy, why does it have the value it does? If it is a field, quintessence, what governs its properties? Could dark energy change over time, transitioning to a phase where it accelerates expansion less, or even reverses? Observations constrain these possibilities but do not eliminate them. The universe's ultimate fate remains uncertain. Perhaps dark energy hints at new physics. String theory and extra dimensions might explain its small value. Perhaps the cosmological constant is anthropically selected. Universes with larger values expand so rapidly that galaxies never form, precluding observers. We exist in a universe with dark energy fine-tuned for structure formation, because only such universes produce beings capable of measuring it. This anthropic reasoning is philosophically contentious, but logically consistent. Or perhaps our understanding of gravity requires revision on cosmological scales. Einstein's equations may be approximations, accurate locally but incomplete globally. This is speculative, but science progresses through questioning even successful theories. So as you drift, as you allow these mysteries to wash gently through your thoughts, reflect on this. We inhabit a universe dominated by unknown forces and substances. Our knowledge is partial, our vision limited, our understanding incomplete. Yet, we persist in asking questions, conducting experiments, refining theories. We stand on the shore of an infinite sea, gathering shells, marveling at their beauty and wondering what lies beyond the horizon. Now let us turn to something more familiar, the living universe, where stars, planets, and chemistry create the conditions for life. Chapter 7, The Living Universe, Stars, Planets, Chemistry, 8430 to 9830. The universe is not merely vast and dark, it is fertile, creative, and productive. Stars forge elements in their cores, scatter them through space, and seed the cosmos with the raw materials for planets and life. This is stellar nucleosynthesis, the cosmic alchemy transforming hydrogen into every element in the periodic table. Stars are born in molecular clouds, vast regions of gas and dust where gravity pulls material together. When a cloud collapses, it fragments into smaller clumps, each potentially becoming a star. As a clump contracts, gravitational potential energy converts to heat. Temperature and pressure rise. Eventually, the core reaches approximately 10 million Kelvin, hot enough for nuclear fusion to ignite. Hydrogen fuses into helium, releasing energy that radiates outward, creating pressure that balances gravity's inward pull. The star enters the main sequence, spending the majority of its life fusing hydrogen. Our Sun, a G-type main sequence star, has burned hydrogen for 4.6 billion years and will continue for another 5 billion. When hydrogen in the core exhausts, fusion ceases. Gravity resumes compression, heating the core until helium fusion ignites, producing carbon and oxygen. The star swells into a red giant. For stars like the Sun, helium fusion is the end. The outer layers drift away, forming a planetary nebula, leaving behind a white dwarf, Earth-sized but sun-massed, composed of electron-degenerate matter, supported by quantum pressure preventing further collapse. Massive stars, more than 8 times the Sun's mass, continue fusing elements. Carbon fuses into neon and magnesium, neon fuses into oxygen and magnesium, oxygen fuses into silicon and sulfur, silicon fuses into iron. Each stage burns faster than the last. Hydrogen fusion lasts millions of years, silicon fusion lasts days. The star develops an onion-like structure, iron core, surrounded by shells of silicon, oxygen, neon, carbon, helium and hydrogen. Iron is the end. Fusing iron consumes energy rather than releasing it. The iron core grows until it exceeds the Chandrasekhar limit, approximately 1.4 solar masses, at which point electron degeneracy pressure fails. The core collapses catastrophically, falling inward at a quarter the speed of light. In less than a second, the core compresses to nuclear density, then rebounds, launching a shockwave that blows the star apart in a core collapse supernova. This explosion releases more energy in a few seconds than the Sun will radiate in its entire lifetime. For weeks, the supernova outshines its entire host galaxy. The blast wave hurls enriched material, carbon, oxygen, iron, gold, into space, seeding the interstellar medium with elements forged in the star's interior and during the explosion itself. Without supernovae, the universe would contain only hydrogen and helium. Planets, life, consciousness, all require elements made in stars. The collapsing core of a supernova forms a neutron star, a city-sized sphere containing more mass than the Sun, composed of neutrons packed to nuclear density. Neutron stars spin rapidly, emitting beams of radiation. If the beam sweeps across Earth, we observe it as a pulsar, a lighthouse in space. The first pulsar, discovered by Jocelyn Bell Burnell in 1967, pulsed every 1.337 seconds, so regular that it was initially nicknamed LGM-1 for little green men, though it was quickly identified as natural. If the core exceeds approximately 3 solar masses, even neutron degeneracy pressure fails. Nothing can halt the collapse. The core becomes a black hole, a singularity surrounded by an event horizon, the ultimate endpoint of gravitational compression. Supernova also produce elements heavier than iron through rapid neutron capture, the R process. Neutrons flood atomic nuclei, which beta decay into heavier elements before more neutrons arrive. Gold, platinum, uranium. every atom heavier than iron formed during supernovae or neutron star collisions, the gold in your wedding ring, the uranium in Earth's core heating the mantle, forged in cosmic violence billions of years ago. Around many stars orbit planets, formed from the same protoplanetary disk that birthed the star. Dust grains collide and stick, growing into pebbles, boulders, planetesimals, and eventually planets. Rocky planets form close to the star, where temperatures vaporize volatile materials. Gas giants form farther out, where temperatures allow ices to condense, providing solid material to grow massive cores that gravitationally capture hydrogen and helium. Our solar system contains 8 planets, dozens of moons, and countless smaller bodies. Jupiter and Saturn are gas giants, composed mostly of hydrogen and helium. Uranus and Neptune are ice giants, rich in water, ammonia, and methane ices. The rocky planets, Mercury, Venus, Earth, Mars, formed in the inner system where metals and silicates could condense. Earth is special not because it is unique, but because it occupies the habitable zone, the region around a star where liquid water can exist on a planet's surface. Water is essential for life as we know it, a universal solvent enabling complex chemistry. Earth's moderate temperature, stable orbit, protective magnetic field, and active geology create conditions conducive to life. But habitability depends on many factors: planetary mass, atmospheric composition, magnetic field strength, stellar type, orbital stability. Too massive, and the planet retains thick hydrogen atmospheres. Too small, and it loses its atmosphere to space. Too close to the star and water evaporates. Too far and it freezes. The habitable zone is a Goldilocks region, not too hot, not too cold, but just right. Thousands of exoplanets have been discovered orbiting other stars. The Kepler Space Telescope, launched in 2009, surveyed a patch of sky for transiting exoplanets, planets crossing their star's face causing periodic dimming. Kepler found over 2,600 confirmed planets and thousands more candidates. We now know that planets are common, that rocky worlds in habitable zones exist around many stars, and that the conditions for life are not rare. Chemistry on planets is governed by the same principles as in laboratories. Carbon, with 4 valence electrons, forms stable, complex molecules, chains, rings, branching structures. Silicon can do this too, but its bonds are weaker at life-compatible temperatures. Carbon is the foundation of organic chemistry, the chemistry of life. Amino acids, the building blocks of proteins, form spontaneously in many environments. The Miller-Urey experiment in 1953 simulated early Earth conditions: water, methane, ammonia, hydrogen, and electric sparks, and produced amino acids. The Murchison meteorite, which fell in Australia in 1969, contains over 70 amino acids, many not found in biology. Chemistry naturally produces the precursors of life. Life on Earth emerged approximately 3.8 billion years ago, within a few 100 million years of the planet's formation. This rapidity suggests life may arise easily given suitable conditions, or perhaps we are the fortunate beneficiaries of a rare event. We do not yet know. So as you rest, as you gently drift through this contemplation of cosmic fertility, consider this. The universe is not dead matter obeying mindless laws. It is creative, productive, and generative. Stars are forges, supernovae are distributors, planets are laboratories, and chemistry is the toolkit. The universe builds complexity, atoms into molecules, molecules into cells, cells into organisms, organisms into ecosystems, ecosystems into biospheres. You are part of this creative process, a conscious node in a universe awakening to itself. Now let us explore the possibility that life is not unique to Earth, that the universe may be teeming with life, perhaps even consciousness beyond our own. Chapter 8. The Possibility of Life, 9830 to 11230. Are we alone? This question has haunted humanity since we first gazed at the stars. For most of history it was philosophy, now it is science. We can estimate, search, and perhaps answer. In 1961, Frank Drake formulated an equation estimating the number of communicative civilizations in the Milky Way. N equals R star times Fp times N E times Fl times Fi times Fc times L, where R star is the rate of star formation, Fp is the fraction of stars with planets, Ni is the number of habitable planets per star with planets, Fel is the fraction of habitable planets where life arises, Fe is the fraction of life, bearing planets where intelligence evolves, FEC is the fraction of intelligent species that develop communication technology, and L is the lifetime of communicative civilizations. Each term is uncertain, but we can estimate. The Milky Way forms approximately 1 star per year. We now know most stars have planets. Fp is close to 1. Kepler data suggest perhaps 20% of Sun-like stars have Earth-sized planets in habitable zones, so only might be 0.2, but Flies, Fe, Fc and L are unknown. Life arose quickly on Earth, suggesting Fl might be high. But we have only one example, ourselves. Perhaps Earth is typical, or perhaps extraordinarily fortunate. Intelligence evolved once on Earth after billions of years of life, suggesting Phi is low, but again, one example is insufficient for statistics. Technology arose once, us, suggesting Fc is low, or perhaps inevitable once intelligence reaches a threshold. And L, human technological civilization is barely a century old. Will we survive another century, another millennium, another million years? L depends on factors we do not yet control. Plugging optimistic values into Drake's equation yields thousands of communicative civilizations in our galaxy. Pessimistic values yield less than 1. We may be alone. The truth lies somewhere between, but where? The Fermi paradox, named for physicist Enrico Fermi, deepens the mystery. If intelligent life is common, where is everyone? The Milky Way is 10 billion years old, given civilizations billions of years to expand and colonize. Even at sublight speeds, a civilization could spread across the galaxy in a few million years. So where are the megastructures, the signals, the evidence? Why is the sky silent? Many solutions have been proposed. Perhaps intelligent life is rare. Earth may be atypical in ways we do not yet recognize. Perhaps intelligence is common, but technology is rare. Most civilizations never develop radio or spaceflight. Perhaps civilizations self-destruct. War, environmental collapse, or existential catastrophe ends them before they colonize. Perhaps they transcend into forms we cannot detect, upload into virtual realities, leave the physical universe, or evolve beyond our comprehension. Perhaps they are hiding, observing without contact, awaiting our maturity. Perhaps the galaxy is a zoo, and we are the uncontacted tribe. Perhaps spacefaring civilization is simply harder than we imagine, and no one has yet succeeded. Or perhaps we are simply early. The universe is 13.8 billion years old, but the first generation of stars contained no heavy elements, no carbon, oxygen, iron. Only after supernovae seeded space with these elements could rocky planets form. Earth-like worlds may have become common only a few billion years ago. We might be among the first technological civilizations to arise. This is the early bird hypothesis, offering hope that the universe may eventually teem with life. But we are pioneers. We search. SETI, the search for extraterrestrial intelligence, scans the sky for radio signals, hoping to detect intentional or accidental transmissions. Since 1960, SETI has conducted thousands of hours of observation, covering millions of frequencies, analyzing billions of potential signals. So far, silence. The famous WOW signal, detected in 1977, a strong narrowband radio signal lasting 72 seconds, remains unexplained but is never repeated. It may have been terrestrial interference, or it may have been something else. We do not know. Breakthrough. Listen. A 10-year, $100 million SETI program launched in 2015 surveys 1 million stars and 100 galaxies across a broad range of frequencies. As of now, no confirmed extraterrestrial signals have been detected. The silence continues, but absence of evidence is not evidence of absence. Perhaps civilizations do not broadcast. Perhaps they communicate via narrow beams or neutrino streams or methods we've not conceived. Perhaps they are there but invisible to current technology. We have searched only a tiny fraction of the sky over a limited range of frequencies for a brief period of cosmic time. Life might also exist in forms we do not recognize. Carbon-based, water-dependent life is all we know, but silicon-based life, ammonia biochemistry, or entirely different principles might operate elsewhere. Titan, Saturn's largest moon, harbours methane lakes and organic chemistry at -180 degrees Celsius, frigid by Earth standards, but perhaps conducive to exotic biochemistry. Europa, a moon of Jupiter, possesses a subsurface ocean beneath an ice shell, potentially heated by tidal flexing, offering a habitable niche. Enceladus, a moon of Saturn, vents water plumes into space, suggesting active hydrothermal vents on its ocean floor, environments that host extremophils on Earth. Life may be common, but intelligent life rare. Single-celled organisms dominated Earth for 3 billion years before multicellular life emerged. Intelligence required billions of years more. Perhaps the leap from microbes to minds is extraordinarily difficult. Perhaps most biospheres remain microbial indefinitely. Or perhaps intelligence is common but ephemeral. Technological civilizations may face existential risks, nuclear war, engineered pandemics, artificial superintelligence misaligned with human values, environmental collapse. If most civilizations self-destruct shortly after achieving technology, the galaxy could be littered with ruins, with only brief windows when signals might be detected. Yet despite the silence, the search continues. The James Webb Space Telescope analyzes exoplanet atmospheres, seeking biosignatures, oxygen, methane, phosphine, chemicals that might indicate life. Ground-based telescopes improve sensitivity. Radio and optical SETI expand. Spacecraft missions explore icy moons. We are looking, listening, reaching out. Perhaps one day we will receive a signal, a pattern in the noise, unmistakably artificial, unmistakably intentional. That day will transform humanity's understanding of our place in the cosmos. We will know we're not alone. We will have neighbours, friends, or perhaps warnings. That day may come in our lifetimes or centuries from now, or never. But the search itself is valuable. It defines our curiosity, our hope, our refusal to accept that the universe's vastness harbours only us. So as you drift, as you rest in contemplation, imagine the possibility. Somewhere, perhaps light years away, perhaps in a galaxy across the cosmos, another mind gazes at the stars and wonders the same question: are we alone? Perhaps that mind sees our sun as a faint point of light and dreams of worlds around it. Perhaps that mind, like you, is conscious, curious, and seeking connection. The universe may be silent now, but silence is not emptiness. It is potential, waiting to be filled. Now, let us turn to the far future, the universe's ultimate fate, where entropy, expansion, and endings await. Chapter 9. The Far Future and Heat Death, 100-1230 to 100-2630. The universe had a beginning. Will it have an end? Not in the sense of ceasing to exist, but in the sense of reaching a final state, a condition from which no further change is possible. This is heat death, the maximization of entropy, the end of complexity and structure. Entropy, the second law of thermodynamic states, always increases in a closed system. Entropy measures disorder, randomness, the spreading out of energy into ever less useful forms. A hot star and cold space have low entropy. Energy is concentrated, available for work. Billions of years later, when the star has radiated its energy into space, that energy has spread uniformly, increasing entropy. Eventually, if the universe is closed, entropy reaches a maximum, and no further energy transfers occur. This is heat death. But the universe's ultimate fate depends on its geometry and composition. If the universe is closed, positive curvature, it will eventually stop expanding and recollapse in a big crunch, reaching infinite density and temperature in a singularity. If open or flat, and if dark energy remains constant or increases, the universe will expand forever, accelerating eternally. Current observations favor eternal expansion driven by dark energy. Assuming this, let us trace the far future. For the next several billion years, the universe changes relatively little. Stars burn, galaxies collide, black holes grow. In approximately 4 billion years, the Milky Way and Andromeda collide. Despite containing hundreds of billions of stars, actual collisions between stars are vanishingly rare. Galaxies are mostly empty space. The collision is gravitational, disrupting orbits, triggering starbursts as gas clouds compress and ignite. Over 1 billion years, the galaxies merge into a massive elliptical Milkomeda. The Sun, now approximately 4.6 billion years old, will remain on the main sequence for another 5 billion years. Eventually, hydrogen in the core exhausts. The core contracts, heats, and ignites helium fusion. The Sun swells into a red giant, engulfing Mercury and Venus, possibly Earth. Outer layers drift away, forming a planetary nebula, leaving behind a white dwarf, slowly cooling over trillions of years. 1 trillion years from now, star formation will have nearly ceased. The universe contains only stars already formed. No new ones are rising. The smallest, longest-lived stars, red dwarfs, burn hydrogen slowly, shining for trillions of years. But eventually even they exhaust their fuel and fade. By 10 to the 14th power years, 100 trillion years, the stelliferous era ends. The last stars flicker out. The universe enters the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, black holes, and planets. White dwarfs cool slowly, radiating stored heat. They are not truly dead. Electron degeneracy pressure supports them indefinitely. Over trillions of years, they cool to black dwarfs, dark and inert, close to absolute zero. Neutron stars likewise cool, supported by neutron degeneracy pressure. Brown dwarfs, failed stars too small to ignite hydrogen fusion, contract and radiate gravitational energy, glowing dimly for billions of years before cooling completely. Now planets, no longer warmed by stars, freeze, atmospheres condense into ices, geology halts, planets orbit dead stars in eternal darkness. But stellar remnants may not last forever. If protons decay, as some grand unified theories predict, even white dwarfs and neutron stars will dissolve. Protons have an observed half-life exceeding 10 to the 34th power years, but if decay occurs at all, by 10 to the 40th power years, stellar remnants will have disintegrated into radiation, leaving only black holes and isolated particles, photons, neutrinos, electrons, positrons. The universe enters the black hole era. Black holes, once considered eternal, evaporate through Hawking radiation. Quantum fluctuations near the event horizon create particle-antiparticle pairs. Occasionally, one falls into the black hole while the other escapes, carrying away energy. The black hole slowly loses mass. The evaporation rate is inversely proportional to mass. Small black holes evaporate quickly, massive ones slowly. A solar mass black hole takes 10 to the 67th power years to evaporate. Supermassive black holes in galaxy centers, billions of solar masses, take 10 to the 100th power years or longer. But eventually even these titans succumb. As they shrink, evaporation accelerates. The final moments are explosive, a burst of Hawking radiation returning the black hole's mass to the universe. By 100 years, most black holes have evaporated. The universe is now filled with photons, neutrinos, and sparse electrons and positrons, separated by unimaginable distances due to cosmic expansion. The average separation between particles exceeds the size of galaxies. The universe is dark, cold, nearly empty. This is the dark era approaching heat death. Temperature approaches absolute zero. Entropy approaches its maximum. No energy gradients exist to drive processes. Structure, complexity, information, all have dissolved. The universe reaches equilibrium, featureless and unchanging. Or does it? Some physicists speculate that even in the far future, rare fluctuations might occur. Quantum mechanics permits temporary violations of energy conservation. Virtual particles borrowing energy from the vacuum for brief moments. Over incomprehensible timescales, these fluctuations might assemble complex structures, perhaps even fleeting pockets of order, ephemeral consciousnesses existing for instance before dissolving back into equilibrium. Roger Penrose proposes conformal cyclic cosmology, CCC, suggesting the universe's end might be its beginning. As matter decays and black holes evaporate, the universe becomes dominated by massless particles, photons. Conformal geometry, which preserves angles but not distances, treats this state as equivalent to the Big Bang. The far future and the distant past are conformally identical, allowing a new Big Bang to emerge from the previous universe's end. Cycles repeat infinitely, each universe giving birth to the next. This remains speculative, but it offers hope that the story does not end with heat death, that the universe might be eternal, cyclical, perpetually renewing. Yet whether the universe ends in heat death, big crunch, or eternal cycles, the far future is unimaginably distant. The current age of the universe, 13.8 billion years, is negligible compared to the timescales discussed. We live in the universe's vibrant youth, a brief flourishing between the hot birth and the cold end. So as you rest, as you allow these timescales to drift gently through your thoughts, consider this. The universe will outlast all human endeavors, all civilizations, all life. Yet this does not diminish meaning. Precisely because time is finite for us, each moment gains preciousness. The universe's ultimate fate does not render the present meaningless. It renders it unique, unrepeatable, sacred in its transience. Now let us turn to the deepest question, not what the universe is, but why anything exists at all. Chapter 10. The deepest mystery. Why anything? 12630 to 14000. We have journeyed from the quantum fields beneath spacetime, through the Big Bang's explosive birth, across galaxies and voids, into the far future and heat death. We have explored what the universe is, how it began, how it evolves, and how it might end. But one question remains, the most profound of all. Why does anything exist? Why is there something rather than nothing? Why these laws of physics and not others? Why is the universe comprehensible, structured, lawful? Why does it give rise to complexity, life, consciousness? This is the deepest mystery. Not what, not how, but why. Throughout history, humans have sought answers. Ancient cultures invoked gods, creators, prime movers. Theology offers purpose. God willed the universe into existence. But this only displaces the question, why does God exist? If God is necessary, why is anything necessary? If God is contingent, what grounds God's existence? Philosophy has grappled with this question for millennia. Parmenides argued that nothingness is impossible. To speak of nothing is to make it something, a contradiction. Therefore being is necessary. Leibniz framed the question as the principle of sufficient reason. Everything has a reason for its existence. But what is the reason for existence itself? Leibniz concluded that God is the necessary being grounding all contingent existence. Human Kant questioned this reasoning, arguing that existence itself may be a brute fact, requiring no explanation. Modern cosmology approaches the question scientifically. Some physicists argue that nothing is unstable. Quantum mechanics permits virtual particles to emerge from vacuum fluctuations. Perhaps the entire universe is a quantum fluctuation, a spontaneous emergence from nothing, borrowing energy from the gravitational field to create matter with total energy remaining zero. This is speculative, but it offers a naturalistic explanation. Lawrence Krauss argues in A Universe from Nothing that the laws of physics themselves explain why something exists. Quantum field theory and general relativity, applied to the universe's earliest moments, predict that universes can spontaneously nucleate from quantum foam. Nothing, in the physicist's sense of zero-energy vacuum, is unstable and will spontaneously generate something. Critics respond that this merely pushes the question back. Why do these laws exist? Why quantum mechanics? Why space-time? Why not different laws? Or none at all? The existence of physical laws is itself something requiring explanation. The fine-tuning problem deepens the mystery. The constants of nature, speed of light, Planck constant, gravitational constant, masses of fundamental particles, strengths of forces, appear finely tuned for complexity and life. Alter any constant slightly, and stars fail to form, or atoms cannot bond, or nuclei are unstable. The universe's fertility seems improbably precise. Several explanations exist. First, necessity. Perhaps the constants must have these values for logical or mathematical reasons we do not yet understand. Perhaps deeper laws constrain them, eliminating arbitrariness. This is elegant but unsupported by current theory. Second, chance. Perhaps we are simply lucky. Given infinitely many possible universes, one will have the right constants by accident, and we observe that one because only such a universe produces observers. This is the weak anthropic principle. We observe a universe compatible with our existence because we could not exist otherwise. Third, the multiverse. Perhaps infinitely many universes exist, each with different constants, and we inhabit one conducive to life. String theory suggests a vast landscape of possible vacuum states, each corresponding to a different universe with different physical laws. Eternal inflation produces infinitely many universes, bubbling off from the inflating substrate. In this view, every possible universe exists somewhere, and we observe a life-friendly one because we could not observe otherwise. The multiverse is controversial. It is not directly testable. Other universes are causally disconnected from ours. Some argue it is not science but metaphysics. Others respond that the multiverse is a prediction of theories developed for other reasons, string theory, inflation, and deserves serious consideration. The anthropic principle is philosophically subtle. It does not explain why the constants have their values. It explains only why we observe these values, yet it carries explanatory power. If infinitely many universes exist, fine-tuning is expected rather than mysterious. We observe a finely tuned universe, not because it is special, but because we are selection effects. Observers necessarily find themselves in observable universes, but even the multiverse does not answer the ultimate question. Why does the multiverse exist? Why quantum mechanics, string theory, inflation? Why these meta-laws rather than others, or none? Perhaps the question is malformed. Perhaps why assumes purposes, intentions, reasons where none exist. Perhaps existence simply is a brute fact, requiring no further explanation. Perhaps, as Wittgenstein suggested, the world is all that is the case, and no deeper explanation is possible or needed. Or perhaps consciousness plays a role. John Archibald Wheeler proposed the participatory anthropic principle. The universe requires observers to become fully real. Quantum mechanics shows that observation collapses wave functions, creating definite outcomes from probabilistic potentials. Perhaps the universe is a self-exciting circuit. Existence brings forth observers. Observers collapse reality. Reality supports observers. The cosmos is a loop, creating itself through conscious observation. This is speculative and controversial, blending physics with philosophy. Yet it resonates with quantum mechanics' observer dependence and cosmology's anthropic considerations. Perhaps the universe is not something we discover, but something we participate in creating. Or perhaps the mystery is insoluble. Thomas Nagel, in The View from Nowhere, argues that some questions exceed human cognitive capacity. Our minds evolved to solve survival problems, not metaphysical riddles. Perhaps asking why anything exists is like asking what is north of the North Pole, a category error applying concepts beyond their domain. Yet the question persists. Humans cannot help but ask why. It is our nature, curious, wondering, seeking meaning. Even if no answer exists, the question itself reveals something profound about us. We are beings for whom existence is not enough. We demand understanding, purpose, connection to something larger. Perhaps the answer is this: the universe exists because it can. Nothingness is absence of everything: laws, space, time, potential. But if even the possibility of existence exists, then existence is inevitable. Possibility itself is something, and from it, everything follows. This is not proof, but poetry. An intuition that being is more fundamental than non-being, that existence is the default state, that nothingness is impossible. Or perhaps the answer is love, not romantic sentiment, but the cosmic principle that draws things together, gravity binding matter, chemistry forming molecules, biology creating organisms, consciousness seeking connection. The universe exists because existence is connection, relationship, the bringing into being of novelty and beauty. This is not science but philosophy, not proof but perspective. In the end, we return to where we began. What is the universe? It is everything that exists. Matter and energy, space and time, laws and patterns, stars and galaxies, planets and life, minds and wonder. It is a process, not a thing, an unfolding, evolving, creative emergence. It is a mystery, not fully known, not fully knowable, yet inviting our curiosity. And you are part of it. You're not separate from the universe, but an expression of it. Atoms aware, matter conscious, the cosmos contemplating itself, the calcium in your bones, the iron in your blood, the carbon in your cells, all forged in stars. The energy animating you came from the sun, which formed from a collapsing molecular cloud, which condensed from the primordial plasma released at the Big Bang. You are continuous with cosmic history, a chapter in a 14 billion year story. So as you rest, as you drift towards sleep, let this truth settle gently into your awareness. You are the universe, localized, conscious, wondering. You are stardust contemplating stars, atoms aware of atoms, the cosmos waking to itself. This is not metaphor. This is physics. Beautiful, precise, and deeply mysterious. You are not alone in the universe. You are the universe experiencing itself, asking its own questions, seeking its own understanding. Rest now. Breathe. The universe holds you, as it always has, as it always will. You are home. We have journeyed through the universe, from quantum fields to galaxies, from the Big Bang to heat death, from the smallest particles to the largest structures, from origins to endings, from mysteries to deeper mysteries. Along the way, we explored spacetime's fabric, inflation's explosive expansion, dark matter's invisible scaffolding, dark energy's accelerating push, stars forging elements, planets harboring chemistry, life's possibility, and the ultimate question: why anything? The universe is vast, ancient, complex, and beautiful. It is also intimate, woven into you, expressed through you, awakening to itself in your consciousness. You're not merely in the universe. You're the universe, localized, aware, contemplating its own nature. If this journey through cosmic scales and timeless questions has brought you wonder, peace, or curiosity, subscribe to Sleep Entangled for more long-form explorations where science meets serenity. Let others discover these contemplative voyages through physics and philosophy, designed for minds seeking both understanding and rest. Thank you for drifting with me through the cosmos. May your dreams carry echoes of quantum fields, stellar forges, and cosmic mysteries. May you rest knowing you are stardust, conscious and curious, part of something far larger, far older, and far more beautiful than any one lifetime can fully comprehend. This is Sleep Entangled, where cosmology and consciousness merge, where science and wonder dance, where the universe contemplates itself. Until we explore together again, rest well, dream deeply, and remember, you are the cosmos, awake and aware. Good night.